Okay, last time we had introduced the operation of addition for Dedekind cuts, and we had proved a certain property C2. So actually showing this operation is well defined, meaning that if you add two Dedekind cuts, you obtain a new Dedekind cut. Okay, so now an exercise 8.6.5, which is part of the homework. You need to complete the proof that a plus b is a cut. So you need to show that a plus b defined in the way we described is a cut. As we mentioned, well, property C2, which is important, well, we already proved that. And we said something about the C1 and C3, but they are more or less routine kinds of proof. And one other thing that you need to show for this exercise is that since we're trying to extend the usual notion of addition, show that the plus is a commutative operation. And you have the associativity property that the addition has for Q and for what we know about the real numbers, which we haven't defined yet, but we've been using it up until now. And so, well, you need to show this thing among other things. Just a quick comment about commutativity. If you look at the definition of a plus b, those are all the real numbers that can be written as a sum of an element in A and as an element in B. But since a plus b is the same as b plus a, just by commutativity of rational numbers, then any number that can be written this way can also be written as a number in B plus a number in A. And that happens to be this set as B plus A. So commutativity should not pose any problem. Now, the important thing that we need to get from this exercise is the fact that there is an identity element. So you're also asked to show, you need to show that the set of negative rational numbers is an identity for plus. And this is natural to consider, because whenever if you want to obtain the same set when we add something to A, so that all the elements that can be obtained as some element in A, plus some the elements in another that they can cut, and if you want that to remain the same, we want to be adding things that are not bigger than 0. Otherwise, you will obtain numbers that are not in the original set. And you know that and this is how you generally proceed when defining things for Dedekind cuts. You know that it cannot contain anything bigger than 0, and in case a natural candidate is something that is smaller than 0, I mean, all the numbers that are smaller than 0, and it has to include all of those numbers because Dedekind cuts have that property that whenever you have one number, then you contain all smaller numbers. So basically, this is a very natural definition for the identity, and it turns out that it works. I mean, for the homework, just make sure to include the proofs of both inclusions, both A plus this set O, Dedekind cut O is contained within the original set A, and that A is contained within the within A plus O. and yeah, and this is and for these inclusions, you need to use the properties of you need to use the fact that A is a cut in order to prove them. And so now the question is additive inverses. So how do we define additive inverses? So we want to define, now since you will have shown that this set O is an additive identity, then what we need to show, we need to define a cut which we will denote minus A. Again, this is just notation. I mean, we're using that notation because we know what to expect. We have to find a cut associated to A. Such that if you add A and minus A, you get the 0 cut. That it can cut defined before, so 0. And one thing actually, one useful comment here is that the natural way of defining it, I mean, well, at least it's not the natural way. I mean, it's just the first thing that probably comes to mind is to define it as a set of rational numbers such that minus R is not in A. In fact, this is part of exercise. This is part B of the exercise 8.6.6. And to give you an idea, so let's consider the real line, so to get an idea. So consider the cut, say 3. I mean the cut associated to 3, so all the numbers, so C3, I mean all the numbers, all the rational numbers that are smaller than 3. if we were to define this as all the rationals such that minus r is not in A, right? So all the numbers such that minus r is not in A, then what would be the problem? Here, what happens if we take a look at the number minus 3 over here? Minus 3 is some r, and minus r, which is equal to 3, is not in C3. So if we were to follow this definition, minus C3 would be the set of rational numbers such that Q is less than or equal to 3. Right, because the property that needs to be satisfied to belong to this definition, this potential definition, this faulty definition of the inverse, is that minus r means all the rational numbers such that minus r is not in A in the original cut. The problem is that we cannot include the endpoint if there's such a thing as an endpoint, and because if not, then that wouldn't be a cut. This is not a cut. We saw that in the last session. This will not be a cut as soon as we add on the endpoint. So if we consider, an interval of 4 minus infinity, comma 3 with 3 included, then that will not be a cut because that will have a maximum. So we cannot allow that. So that's the reason we need to be a little bit more careful when defining the additive inverse. This is part of the questions you need to answer for exercise 8.6.6. Okay, but the answer for that part B is essentially that. You don't want to include the endpoint. That's problematic about it. But what you can ask is that isn't the set is instead, which accomplishes the same thing. If we go back to this example, just that it avoids 3 by prescribing that the rational number is smaller than some minus t, where t is some number that is not in A, so smaller than some number, some number to the minus t, where t is a number that doesn't belong to the cut. So that accomplishes that, and it avoids having to include the endpoint. Of course, so when we define the inverse, we don't want that definition to give us something that's not a cut. Otherwise, we will not be able to operate. So the operations and everything that we do for cuts must be completely self-contained within those subsets of the rational numbers. if not, then there's no inverse among Dedekind cuts for arbitrary Dedekind cuts. So what is a good definition then? Instead, given a Dedekind cut A, we define minus A to be the set of rational numbers in Q such that R is less than minus T for some T that is in Q but T is not in A. Okay, so the good thing here is that we are never ever considering something that is potentially in the set. I mean, we will not be including, say, possible endpoints, so maxima here. And part of now, going back to the exercise 8.6.6. So in exercise 8.6.6, you are asked to show that minus A defined in this way is a cut, and that it has the desired property that A plus minus A is a zero cut. Okay, so then we have addition. We have the existence of an identity element, and now we have defined an inverse. Okay, and that will basically be it for this operation, except that we need to define a product now that we'll need to distribute with respect to this recently defined operation of plus. We'll introduce the product operation in the next video. The only reason why this would be a little bit more complicated perhaps is because we have this property with rational numbers. When we multiply negative numbers, we get a positive number. So we need to separate basically definition, and we deal first with non-negative cuts. And then we cook up everything so that we have all the properties we want the product. That will be done next.